There's something haunting about the silence of the universe, not the absence of sound, but the secrets it holds just beyond our reach. For centuries, we've trained our telescopes and tuned our radios to the cosmos, searching for answers in the noise of stars and galaxies. But what if the most profound truths aren't shouting at us? What if they're barely whispering, hidden in the spaces between the signals, so subtle that even science almost passed them by? Today, we're pulling back the curtain on 29 astonishing discoveries, truths buried in the universe's quiet, waiting to be heard. These aren't just minor footnotes in the story of space. They're revelations that could rewrite the textbooks, challenge our understanding of reality, and even hint at possibilities we've never dared to imagine. Think about the last time you stood outside on a clear night, staring up at the stars. It's easy to feel small, humbled by the vastness overhead. But here's the thing, that vastness isn't empty. It's teeming with mysteries we're only beginning to grasp. Dark matter, cosmic anomalies, gravitational ripples, phenomena so elusive that they slipped through the cracks of mainstream science for decades. Why? Because the universe doesn't always reveal its secrets loudly. Sometimes, the most groundbreaking truths are hidden in the quietest corners, disguised as background noise or dismissed as glitches. Until someone looks closer, until someone listens, that's where this journey begins. Together, we'll explore the overlooked, the nearly missed, the whispers in the cosmic static that could change everything. From forgotten data buried in old research papers to strange signals that defied explanation, these 29 truths are more than just curiosities, they're keys to unlocking a deeper understanding of the cosmos. And by the time we're done, you'll never look at the night sky the same way again, because the universe isn't just speaking to us, it's been speaking all along. We just had to learn how to listen. Imagine a sculptor shaping clay without ever touching it, hands hovering just above, invisible but undeniable in their influence. That's dark matter. It doesn't glow, reflect, or cast shadows, yet it bends the very fabric of the cosmos with its gravitational pull. For years, astronomers scratched their heads over galaxies spinning too fast, their outer stars whirling as if gripped by some unseen hand. The math didn't add up until they dared to consider the unthinkable, that most of the universe's matter wasn't just hiding in the dark, it was the dark. What's even stranger, dark matter might be weaving its own secret architecture. Supercomputer simulations reveal vast, delicate filaments stretching across the emptiness between galaxies, a cosmic web where ordinary matter, the stuff we can see, is just the glitter sprinkled on its threads. These hidden structures could explain why galaxies cluster like beads on a string, drawn together by gravity's silent choreography. But here's where it gets wild. Some theories suggest these filaments might be more than scaffolding. They could be bridges, doorways to realms beyond our own, where the laws of physics play by different rules. Yet the most humbling thought isn't just that dark matter exists. It's that we almost ignored it. Early astronomers wrote off those two fast stars as miscalculations, dismissing the whispers of an invisible universe. It took decades of stubborn anomalies, of data that refused to fit the mold, before science finally listened. And now, we're left wondering what else we've been brushing aside, what other truths might be woven into the quiet between the stars. Because if dark matter teaches us anything, it's that the universe's loudest revelations often come in the softest voices. Quantum fluctuations are the universe's best-kept secret, a silent hum beneath the surface of reality itself. Picture a calm lake at night, its surface smooth and still. Now imagine that same lake, but zoomed in 1,000,000 times closer. Suddenly, it's not so calm. Tiny ripples appear and vanish in an instant, as if the water itself is alive with invisible energy. That's what empty space is really like. It's not empty at all. It's a seething, bubbling quantum foam where particles blink into existence and disappear faster than we can measure, borrowing energy from the future only to pay it back in an instant. For decades, this was just a wild idea scribbled on blackboards, a mathematical curiosity with no proof. Then came the experiments. Scientists watched as atoms jittered unpredictably, nudged by forces that shouldn't exist. Telescopes captured galaxies forming in ways that defied gravity's rules unless something else was at play. That something, the ghostly push and pull of quantum fluctuations, shaping the cosmos from the smallest atom to the largest supercluster. But here's where it gets mind-bending. Some physicists believe these flickering particles aren't just random noise. They might be the universe's hidden language, lines of code written into the fabric of space-time itself. Think of it like glitches in a video game, tiny errors that reveal the underlying program. What if every time a particle winks in and out of existence, it's actually running a subroutine in the grand cosmic algorithm? Decoding these fluctuations could be like finding the universe's source code, exposing the rules that govern everything from the spin of an electron to the birth of black holes. And the wildest part, we almost missed it. Early quantum theorists dismissed these fluctuations as mathematical artifacts, quirks of the equations with no real-world meaning. It took stubborn anomalies, atoms that wouldn't sit still, energy that appeared from nowhere, to prove the universe was whispering its secrets in a language we barely understood. Now, as we listen closer, we're left wondering, if empty space isn't empty, what else have we gotten wrong? Because if quantum fluctuations teach us anything, it's that the universe loves to hide its greatest truths in plain sight. Back in the 1970s, as NASA Pioneer probes sailed through the void beyond our solar system, something strange happened. These spacecraft, designed to obey the laws of motion as we understood them, began slowing down more than they should have. It was as if an invisible hand had reached out and gently tugged them backward, a force unaccounted for by gravity, friction, or any known physics. Engineers checked and rechecked the numbers, but the anomaly persisted. Yet instead of sparking a revolution in science, it was quietly filed away, dismissed as a quirk of thermal radiation pushing against the probes. For decades, the Pioneer anomaly gathered dust in the archives, a cosmic mystery waiting for someone to take it seriously. Then, decades later, a fresh pair of eyes revisited the data. What if that tiny deceleration wasn't just an engineering glitch? What if it was the universe whispering a secret? Some researchers now believe the probe's unexpected slowdown could be evidence of something far more profound, either a flaw in Einstein's theory of gravity, or even a glimpse into hidden dimensions curled up within our own. Imagine space not as a smooth, three-dimensional sheet, but as a folded origami of unseen layers, each exerting its own subtle tug on matter. The pioneers, drifting through this hidden landscape, might have brushed against forces we're only beginning to conceive. Here's what makes this so thrilling. The probes weren't built to study these effects. They weren't looking for anomalies. They were simply messengers carrying humanity's first robotic emissaries into the unknown. Yet in their quiet, unassuming way, they stumbled upon something extraordinary. The faintest deviation in their speed, a discrepancy smaller than a single millimeter per second squared, could be the first clue to a physics we've never dreamed of. It's like finding a single misplaced stitch in a tapestry, and realizing it unravels the entire pattern. And the most haunting question, how many other signals have we ignored? How many other probes, telescopes, or experiments have recorded data that didn't fit, only to be labeled as noise and forgotten? The pioneers remind us that sometimes the most revolutionary discoveries aren't made by what we're actively searching for, but by what we weren't even looking to find. Their silent distress call, buried in decades-old telemetry, might just be the universe's way of telling us we've only scratched the surface. Oumuamua wasn't supposed to move like that. When this strange, cigar-shaped visitor from another star system streaked through our solar system in 2017, astronomers expected it to follow the predictable arc of a comet or asteroid, coasting on gravity's pull. But it didn't. Instead, it sped up slightly as it raced away from the sun, as if pushed by an unseen force. At first, scientists scrambled for conventional explanations. Maybe it was outgassing, the kind of material vaporizing from a comet's surface that creates a glowing tail. Except Oumuamua had no tail, no visible plume of gas or dust. Just that inexplicable, unnerving acceleration, like a sail catching a cosmic breeze. The more researchers studied it, the stranger it became. Its shape, an elongated sliver roughly 10 times longer than it was wide, was unlike any natural space rock we'd ever seen. Its surface, oddly reflective, suggested a metallic sheen, and then there was its trajectory, slicing through the solar system at an angle so steep it couldn't have originated here. This wasn't just a visitor from another star. It was a messenger from the void, carrying secrets we didn't know how to read. Some dared to voice the unthinkable. Could Oumuamua be artificial? A fragment of alien technology, perhaps a solar sail propelled by starlight. The hypothesis sent shockwaves through the scientific community, met with equal parts fascination and skepticism. After all, extraordinary claims require extraordinary evidence. But here's the troubling part: we'll never know for sure. By the time astronomers spotted Oumuamua, it was already speeding away, too distant for follow-up observations. The window to study it had slammed shut, leaving us with grainy telescope images and a mountain of unanswered questions. Recent computer simulations have offered new possibilities. Exotic ices made of molecular hydrogen or nitrogen could explain the acceleration without outgassing visible to our instruments. Yet even these theories feel like patches on a deeper mystery. Because the real lesson of Oumuamua isn't just about one strange object. It's about how quickly we dismiss what we don't understand. For centuries, humanity has dreamed of contact with other civilizations. But when something truly anomalous arrived on our cosmic doorstep, we fumbled the encounter, too bound by old assumptions to recognize the extraordinary. What lingers isn't just curiosity about Oumuamua's origins. It's the chilling realization that the next interstellar visitor might already be on its way. Will we be ready, or will we again explain away the impossible, missing the whispers of the universe because we weren't truly listening? Oumuamua was a test, one we might not have passed. But its greatest gift could be the humility it leaves behind, a reminder that the cosmos is far stranger than our textbooks dare to suggest. The cosmic microwave background is like the universe's baby picture, a snapshot of the cosmos when it was just 380,000 years old. Its glow stretched and faded over billions of years into the faint microwave hum we detect today. For decades, scientists treated this afterglow as a uniform canvas, its tiny temperature variations explained as the seeds of galaxies, random quantum fluctuations amplified by time. But then something odd emerged. Hidden in the data were patterns too precise, too symmetrical to be accidental. Some regions of the sky mirrored others with eerie similarity, as if the universe had folded in on itself. Other patches showed strange alignments, cosmic axes where temperatures lined up in ways that defied the rules of randomness. At first, researchers brushed these anomalies aside, chalking them up to instrument error or statistical flukes. After all, the universe wasn't supposed to have a preferred direction. Then artificial intelligence entered the picture. Machine learning algorithms, trained to sift through the noise, began flagging structures in the cosmic microwave background that human eyes had overlooked. Some resembled scars, bruises left by collisions with other universes in a vast multiverse. Others hinted at concentric rings like ripples from a pebble dropped into a pond, suggesting our Big Bang might not have been the first. The most startling discovery: cold spots, vast, unexplained regions where the microwave background dips in temperature, as if something had siphoned away energy on a scale we can barely comprehend. One theory posits these could be imprints of black holes from a previous cosmic cycle, relics of a universe that existed before our own. What's unsettling isn't just the existence of these patterns. It's how long we missed them. For years, the data sat in plain sight, dismissed as noise because it didn't fit the standard model. Even now, some scientists argue these anomalies are mere coincidences, the cosmic equivalent of seeing faces in clouds. But the more we look, the harder that explanation becomes to defend. If the universe were a book, these patterns might be marginalia, notes scribbled in the margins by forces beyond our understanding. And the implications, they're staggering. If the cold spots truly trace the outlines of a pre-Big Bang universe, it would mean time didn't begin 13.8 billion years ago. It rebooted. Our cosmos could be one page in an infinite library of cycles, each ending in collapse and rebirth. The symmetries, meanwhile, suggest something even more radical, that the laws of physics might not be universal. Those mirrored regions could be places where space-time itself is knotted, threading through higher dimensions we can't perceive. The cosmic microwave background was supposed to be a solved puzzle, a relic we'd decoded. Instead, it's become a mirror reflecting back questions we never thought to ask. And as AI peels back layer after layer of hidden structure, one thing grows clear: the universe's first light might also be its most profound cipher, whispering secrets about realities beyond our own. We're not just mapping the afterglow of creation, we're reading between the lines of existence itself. Time doesn't tick the same everywhere. Einstein showed us over a century ago that gravity doesn't just bend space, it stretches time itself, slowing clocks near massive objects like planets or stars. But the real magic happens when gravity becomes extreme, near a black hole where space-time curves so sharply that not even light can escape. Time doesn't just slow down. It practically grinds to a halt. From the perspective of someone watching from a safe distance, a clock falling into a black hole would appear to freeze at the event horizon, its hands never reaching the next second. Yet for the person holding that clock, time would feel perfectly normal, even as the universe around them speeds into fast forward. This isn't just theoretical. Right now, orbiting Earth, satellites carry atomic clocks precise enough to catch space-time in the act, and they've spotted something peculiar. These clocks don't quite stay in sync with their counterparts on the ground. They run slightly faster, gaining about 45 microseconds per day, proof that Earth's gravity tugs at time itself. But here's where it gets weirder. Some of these time discrepancies don't match our planet's predicted gravitational pull. Tiny, unexplained delays suggest hidden masses warping spacetime in ways we can't yet see. One leading theory points to dark matter. If invisible clumps of it lurk near Earth, their gravity could be subtly bending time, creating those microsecond hiccups in satellite data. Another possibility: primordial black holes, ancient, city-sized remnants from the Big Bang drifting unseen through our solar system. Each would weigh as much as a mountain, warping spacetime around it like a hidden whirlpool. Either way, these time anomalies might be more than glitches. They could be the universe's way of sketching a map to its darkest, most elusive structures using time itself as the pen. The most humbling part, we almost missed it. Early satellite engineers treated these timing quirks as nuisances, correcting for them without asking why they existed. It took decades before someone realized these weren't errors to fix but clues to follow. Now, researchers are treating space-time like a cosmic detective story, searching for the fingerprints of hidden mass in the way seconds stutter and stretch. And the implications stretch far beyond our orbit. If we can decode these subtle time warps, we might finally pinpoint dark matter's hiding places or catch a primordial black hole drifting past. More profoundly, it suggests that time isn't just a backdrop to the universe's drama. It's an active player, bending and twisting in ways that reveal secrets no telescope could ever see. Every tick of a clock isn't just marking moments, it's carrying whispers from the invisible architecture of reality itself. So next time you check your watch, consider this: the flow of time isn't as constant as it feels. It's a river shaped by the unseen landscapes it passes through, and somewhere out there, in the gaps between seconds, the universe might be hiding its greatest mysteries, not in the roar of colliding galaxies, but in the silent, imperceptible stretching of time. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. A single neutrino could sail through a block of lead light years thick without slowing down. But here's the twist: these phantoms have a habit of shape-shifting. One moment they're electron neutrinos, the next they've morphed into muon or tau neutrinos, swapping identities mid-flight as if reality itself is playing a shell game. When scientists first spotted this behavior in the 1960s, they brushed it off as a quirk, a minor puzzle to solve later, but the deeper they looked, the more unsettling it became. Neutrinos weren't just breaking the rules, they were rewriting them. The key to this mystery lies in mass. For decades, the standard model of particle physics insisted neutrinos were massless, zipping through space at the speed of light. But if that were true, they couldn't oscillate between flavors. The fact that they do means they must have some tiny, almost imperceptible weight. A revelation that cracked open one of physics' most stubborn doors. Suddenly, the rulebook needed an update. Either the standard model was incomplete or something far stranger was at play. Hidden particles, unseen forces, even extra dimensions, all became fair game to explain why neutrinos refused to sit still. The real shock came when researchers dug into old data from nuclear reactors. Buried in the noise of decades-old experiments were patterns that shouldn't have existed, hints that neutrinos might be interacting with something beyond the known particles. Some theories now suggest these oscillations could be whispers from the dark sector, a hidden realm of particles that make up dark matter and dark energy. Imagine neutrinos as messengers flitting between our world and this shadow universe, carrying secrets in their fleeting transformations. What's wildest isn't just the science. It's how close we came to missing it. Early experiments dismissed neutrino oscillations as measurement errors, their results filed away as curiosities. It took 30 years and detectors buried deep underground, shielded from cosmic interference, to prove the phenomenon was real. Now, as we study these shape-shifters more closely, we're left with a haunting thought. If neutrinos are this strange, what else have we overlooked? Their oscillations might be more than a particle physics puzzle. They could be the first faint signals of a universe far richer and weirder than we ever imagined. One where the rules we take for granted are just the surface of something much deeper. And the implications stretch beyond theory. If neutrinos really are tugging at the curtains of dark energy, understanding their dance could explain why the universe is expanding faster than it should be. These tiny, nearly massless particles might hold the key to the cosmos' ultimate fate, whether it ends in ice or fire, collapse or eternal drift. All this from a particle so ghostly it barely notices our existence. The lesson: sometimes the universe hides its biggest truths in the smallest, quietest places, and if we're willing to listen, even the faintest whispers can change everything. The Boötes Void isn't just empty, it's unnervingly so. Picture a sphere of darkness so vast it could swallow thousands of galaxies, a cosmic desert stretching over 300 million light-years across with barely a handful of stars to break the monotony. When astronomers first mapped this region in the 1980s, they assumed their instruments had failed. The universe, after all, isn't supposed to have holes like this. Matter should be distributed in a web-like pattern with clusters and filaments woven together by gravity, but the Boötes Void defies that logic. It's not just a gap in the cosmic tapestry, it's a tear. What makes this emptiness so unsettling is how it mocks our understanding of galaxy formation. According to simulations, regions this large shouldn't exist. The Big Bang's afterglow shows tiny fluctuations in density, seeds that grew into galaxies and clusters, but the void scale dwarfs those variations. It's as if someone took an eraser to a quarter of the observable universe, scrubbing away matter with surgical precision. Some theorists suggest this could be the imprint of an ancient collision, our universe brushing against another bubble in the multiverse, leaving behind a bruise in the form of nothingness. Others propose it's a relic of cosmic inflation, a frozen pocket where space expanded too fast for matter to keep up. Then there's the silence. When telescopes point toward the void, they don't just see darkness, they hear it. The absence of galaxies means an absence of the radio chatter that fills the cosmos, a hush so profound it feels intentional. It's not just empty space, it's space that seems to resist being filled. Recent surveys have spotted a few lonely galaxies drifting in the void, but their oddities isolated, misshapen, as if whatever carved this emptiness left behind stragglers too stubborn to vanish. The most humbling part, we nearly wrote it off. Early astronomers dismissed the void as a statistical fluke, a trick of incomplete data. Even now, some simulations struggle to recreate it without invoking exotic physics. Yet there it sits, a billion light-year question mark demanding an answer. If the void is a scar, it's one that challenges our deepest assumptions. Maybe the universe isn't just expanding, maybe it's unraveling, with voids like this as the loose threads. Or perhaps it's a signpost pointing toward forces we've yet to name. One thing's certain, the Boötes Void isn't just a lack of something. It's a presence, an active, almost defiant reminder that the cosmos still holds mysteries too large to ignore. And as we stare into that abyss, we're left to wonder, is the universe hiding something in that darkness, or is the darkness itself the message? White holes sound like something ripped straight from science fiction, cosmic fountains spraying matter and light into the universe instead of swallowing them whole. Yet they weren't dreamed up by a novelist. They emerged naturally from Einstein's equations as the mirror image of black holes, their theoretical opposites. Where a black hole's gravity is so strong nothing escapes, a white hole would repel everything, spewing out energy and matter with unstoppable force. For decades, physicists dismissed them as mathematical curiosities, impossible oddities with no place in the real universe. But what if we've been wrong? What if white holes aren't just possible but lurking in plain sight? The revival of white holes comes from an unlikely source, the quest to unite quantum mechanics with gravity. In some quantum gravity models, black holes don't last forever. Over unimaginable timescales, they might evaporate through Hawking radiation or transform. Picture a black hole not as a one-way street but as a tunnel. At the end of that tunnel, a white hole bursting into existence as the black hole's demise. Some theories even suggest our own Big Bang could have been the explosive birth of a white hole, a violent release of energy from a collapsing universe in another dimension. It's a dizzying thought that every black hole in our cosmos might someday blossom into a new universe, its death giving rise to another's birth. Then there's the gamma-ray connection. Astronomers have long puzzled over brief, intense flashes of gamma rays, some lasting just milliseconds, others lingering for hours. Most are chalked up to colliding neutron stars or supernova. But a handful defy explanation, their energy signatures too clean, too symmetrical to fit known astrophysical events. Could these be the birth cries of white holes? When a white hole erupts into existence, calculations suggest it would release a staggering pulse of radiation, fading rapidly as the hole stabilizes. The timing, the energy profiles, they're uncannily close to certain anomalous gamma-ray bursts we've already recorded. The irony is palpable. For years, white holes were relegated to textbooks as mathematical ghosts, dismissed because they violated our intuition about how the universe should work. Yet the more we learn, the clearer it becomes. The universe has little patience for our intuitions. Dark matter, quantum entanglement, black holes themselves, all were once deemed impossible until the cosmos forced us to reconsider. Now, as quantum gravity theories breathe new life into white holes, we're left with a humbling possibility. The universe might be peppered with these cosmic fountains, their existence hidden not because they're rare, but because we weren't looking for them. And that's the real lesson here. Science advances not just by confirming what we expect, but by daring to explore what we've been taught to ignore. White holes remind us that even Einstein's equations have secrets left to reveal, that the universe's most profound truths might be hiding in the very ideas we once laughed away. So the next time a gamma-ray burst flickers across the sky, consider this. It might not be a star's death throes. It could be the universe's way of whispering, "You haven't seen everything yet." Fast radio bursts are the universe's most enigmatic postcards, blisteringly bright signals that flare for mere milliseconds, packing more energy than the sun emits in days. When astronomers first detected them in 2007, the assumption was straightforward: cosmic cataclysms like neutron stars colliding or black holes shredding magnetic fields. But then the bursts started repeating, not randomly, but in patterns so precise they seemed almost intentional. Some pulse with intervals separated by exact multiples of 187.5 seconds, like a metronome ticking across billions of light years. Others arrive in clusters, their timing too orderly to be natural chaos. Suddenly, the simplest explanations crumbled, leaving room for something far more extraordinary. Theories now span from the plausible to the mind-bending. Magnetar's ultra-dense, highly magnetized neutron stars remain the leading suspect. Their crust quakes potentially capable of generating these cosmic sirens. Yet even the most violent stellar phenomena struggle to explain the burst's eerie regularity. That's where the wilder ideas creep in. Could these be alien beacons, deliberate signals from civilizations advanced enough to harness entire stars as lighthouses? The energy required would be staggering, but not impossible for a Kardashev Type 2 civilization bathing in the power of a Dyson sphere. Even stranger, some models suggest fast radio bursts might be the exhaust trails of light sails, interstellar ships riding beams of energy across galaxies. Then there's the space-time angle. Certain bursts exhibit frequency sweeps, their radio waves stretching as if dragged through invisible cosmic molasses. One explanation: the signals might be threading through wormholes, their frequencies warped by shortcuts in the fabric of reality. Others propose these bursts are the universe's plumbing, leaks from colossal structures like cosmic strings, defects left over from the Big Bang vibrating like snapped guitar strings. But the most haunting clue lies in what's missing. Between bursts, the silence isn't empty, it's structured. Some sources emit only during specific cosmic windows, falling quiet for years before flaring again on schedule. It's as if whatever's producing them operates on cycles we can't yet decipher, a language written not in the bursts themselves, but in the gaps between them. What's remarkable isn't just the mystery, it's how close we came to dismissing it. Early repeating bursts were initially written off as terrestrial interference, cell towers, or satellite glitches. Even now, some astronomers resist the more exotic theories, arguing extraordinary claims require extraordinary evidence, but history has a way of humbling our assumptions. Pulsars, after all, were once mistaken for alien signals until their natural origins were uncovered. The lesson: sometimes the universe's most ordinary phenomena wear the guise of the impossible, and vice versa. As telescopes like CHIME and FAST scan the skies, catching hundreds of new bursts each year, one truth becomes clear: these aren't just cosmic oddities. They're probes testing our willingness to question what we think we know. Whether natural or engineered, fast radio bursts defy easy categorization. And that's what makes them so thrilling. In their fleeting brilliance, they illuminate not just the depths of space, but the limits of our imagination. The real question isn't just what they are, it's what they're daring us to consider next. Galaxies aren't supposed to defy gravity's rules, yet here we are, staring at cosmic rebels that refuse to play along. Take NGC 1052DF2, a wispy galaxy so transparent you can practically see right through it. When astronomers measured its star's motion, they expected the familiar dance dictated by dark matter's invisible grip. Instead, they found chaos. The stars moved sluggishly, lazily, as if whatever unseen anchor typically holds galaxies together had simply let go. No dark matter. No hidden mass, just stars adrift in a gravity-defying puzzle. This wasn't supposed to happen. Dark matter has been the universe's scaffolding for decades, the go-to explanation for why galaxies don't fly apart. Its gravitational pull keeps spinning disks of stars from unraveling, like an invisible hand steadying a wobbly top. But these oddball galaxies, now numbering over a dozen, spin too slowly, their stars too relaxed, as if dark matter never showed up to work. At first, scientists dismissed them as flukes. Maybe their measurements were off, maybe nearby galaxies were distorting their motion. But with each new discovery, the anomaly grew harder to ignore. Here's where it gets thorny. If dark matter isn't universal, what's holding these galaxies together? One radical theory suggests we're seeing the fingerprints of modified Newtonian dynamics, MOND for short. This controversial idea tweaks the laws of gravity itself, proposing that on cosmic scales, gravity behaves differently than Einstein predicted. In MOND's universe, there's no need for dark matter because gravity gains an extra kick when accelerations become tiny, like those at a galaxy's faint outskirts. It's a bold claim, one that would upend a century of astrophysics, but these ghostly galaxies, they fit MOND's predictions eerily well, yet there's a catch. For every galaxy that moves too slowly, there's another like the Dragonfly 44, a cosmic leviathan with stars so sparse it should have evaporated eons ago. Instead, its stars whip around at breakneck speeds, implying a dark matter halo hundreds of times more massive than the visible galaxy. How can dark matter be absent in one galaxy and overwhelmingly present in another? The contradiction cuts to the heart of cosmology itself. Either our understanding of dark matter is catastrophically incomplete, or gravity isn't the steadfast force we've always assumed. Perhaps the most intriguing clue comes from the galaxies caught in the act of losing their dark matter. In the NGC 1052 group, astronomers found two galaxies with identical stellar masses but wildly different motions, one firmly anchored by dark matter, the other nearly free of it. The culprit, a violent galactic collision, may have stripped the dark matter from one, leaving behind a naked galaxy of stars. If true, it suggests dark matter isn't just a passive backdrop but something that can be torn away, like a coat ripped off in a cosmic wind. What's clear is this: the universe refuses to be boxed into simple explanations. These outliers, whether missing dark matter or drowning in it, aren't mistakes. They're messages. Maybe dark matter comes in multiple flavors, some sticky and some slippery. Maybe gravity itself is more flexible than we've dared to imagine. Or perhaps, just perhaps, we're glimpsing the edges of a larger truth, one where the universe's rules aren't uniform, but as varied as the galaxies themselves. The lesson here isn't just about dark matter. It's about the danger of assuming we've cracked the cosmic code. For every rule we write, the cosmos seems to scribble an exception in the margins. And in those exceptions, if we're brave enough to look, might lie the next revolution in our understanding of reality. The moon shouldn't have a magnetic field, at least not one strong enough to leave scars in rock. With a core barely a quarter of Earth's size, our lunar companion lacks the churning metallic heart needed to sustain a planet-scale dynamo. Yet when Apollo astronauts brought back samples in the late 1960s, the evidence was undeniable. Tiny mineral grains in those rocks were magnetized, their atomic compasses frozen in time, pointing toward an era when the moon's surface crackled with a magnetic force nearly as strong as Earth's. Scientists were baffled. Some dismissed it as contamination, an artifact of lunar material interacting with Earth's field during transport. Others quietly filed the data away, labeling it an unsolvable anomaly. But the truth was far stranger than anyone imagined. Decades later, high-resolution scans of those same rocks revealed something astonishing. The magnetization wasn't random or scattered, it told a story. Certain crystals aligned in ways that recorded not just the presence of a magnetic field, but its dramatic rise and fall. For roughly 500 million years, the moon's field pulsed with unexpected strength before vanishing entirely. This wasn't a fluke, it was a cycle. The question wasn't just how a tiny core could generate such power, but why it flickered like a light bulb on its last legs. Computer simulations now offer two electrifying possibilities. The first involves a lunar dynamo on steroids. Imagine the moon's core as a pot of molten metal, stirred not by the slow, steady rotation we see today, but by violent cosmic turbulence. Early in its history, the moon orbited much closer to Earth, its interior stretched and kneaded by gravitational forces. This tidal heating, combined with radioactive decay, might have supercharged convection in its core, spinning up a magnetic engine fierce enough to imprint rocks, but too unstable to last. The second theory is where things get cosmic. Some researchers propose the moon's field wasn't homegrown at all. Instead, it could have been borrowed, a temporary gift from Earth during a rare orbital dance. When planetary magnetic fields interact, they can create tangled, amplified zones of force. If the young moon passed through one of these magnetic knots, its surface might have soaked up the field like a sponge, trapping the energy in minerals before it faded. Yet the most tantalizing clue lies in timing. The moon's magnetic heyday overlaps eerily with a period when Earth's own field underwent wild fluctuations. Coincidence or evidence of a celestial tango where the two worlds exchanged more than just gravity? The rocks don't lie. They're whispering secrets about a time when the moon wasn't the quiet neighbor we know today, but a dynamic player in Earth's early drama. What's haunting isn't just the mystery of how this happened, it's how close we came to missing it entirely. Those Apollo samples sat in vaults for years, their magnetic fingerprints overlooked because they defied textbook wisdom. Now, as new missions prepare to drill deeper into lunar geology, we're left wondering what other surprises are buried in the dust. The moon's lost magnetism isn't just a puzzle about the past. It's a reminder that sometimes the universe's quietest objects hold the loudest secrets, and if we're willing to listen, even the most familiar worlds can shock us. Titan is a cosmic paradox wrapped in a nitrogen haze, a world where rivers carve valleys not with water, but with liquid methane, where sand dunes tower hundreds of feet high yet aren't made of silicate but frozen hydrocarbons. This alien landscape, Saturn's largest moon, shouldn't exist, at least not for long. Here's why: Titan's thick atmosphere is packed with methane, a gas that sunlight should break apart within 50,000 years. Yet Titan's skies have persisted for billions. Like a car running on an empty tank, this moon defies the laws of chemistry, leaving scientists scrambling to find the hidden fuel source keeping its engine alive. For years, the leading theory pointed to Kano's ice-spewing vents that might replenish methane from deep underground. But when NASA Cassini probe mapped Titan's surface in infrared, the expected hotspots were nowhere to be found. No smoking guns, no plumes of icy fury, just silence. Then came the lab experiments. Researchers simulating Titan's upper atmosphere found something startling. When they zapped nitrogen and methane with UV light, the mix didn't just produce the expected organic haze. It created molecules like vinyl cyanide compounds that, on Earth, are linked to the formation of cell membranes. Suddenly, Titan's missing methane wasn't just a puzzle. It was a clue. The real twist lies in what Cassini didn't see. Buried in the probe's radar data were hints of vast underground reservoirs, liquid layers sloshing beneath Titan's icy crust. Some models suggest these hidden seas could be methane's secret stash, slowly leaking gas upward to replenish what sunlight destroys. But there's another, far wilder possibility. What if Titan's methane isn't geologic at all? On Earth, methane is a byproduct of life belched out by microbes in swamps and cow guts. Could Titan's lakes be fed by alien organisms, their metabolism tuned not to oxygen or sunlight, but to the moon's frigid, chemical-rich depths? Here's where it gets eerie. In 2023, researchers studying Titan's atmospheric chemistry stumbled upon an anomaly. The concentration of certain organic molecules fluctuated in ways that couldn't be explained by known physics. The patterns weren't random. They followed cycles, seasonal, rhythmic, almost like the breathing of something alive. Of course, the scientific community urged caution. Extraordinary claims require extraordinary evidence, but the data refused to sit quietly. If this were Earth, we'd call it a biosignature. On Titan, it's a riddle wrapped in an enigma, floating in a sea of liquid methane. The most humbling thought isn't that Titan might harbor life. It's how close we came to dismissing its mysteries as mere quirks of chemistry. For decades, planetary scientists treated Titan as a frozen time capsule, a relic of early Earth's conditions. But the deeper we look, the clearer it becomes. This moon isn't a museum. It's a laboratory, one where the rules of biology, if they apply at all, might be written in solvents we've never imagined. Every unexplained molecule in its atmosphere, every odd fluctuation in its lakes, is a whisper from a world that refuses to fit our templates, and that's the real magic of Titan. Its silence isn't empty, it's pregnant with possibility. Whether the answer lies in hidden geology or shadow biospheres, one thing's certain: this moon has been guarding its secrets behind a veil of nitrogen and methane for billions of years. Now, as new missions prepare to drill beneath its ice and sail its alien seas, we're finally learning to listen not just to the noise of the cosmos, but to the whispers in between. Titan isn't just a moon, it's a question written in chemistry waiting for us to find the answer. The Hubble tension isn't just a scientific disagreement, it's a cosmic riddle threatening to crack the foundation of modern cosmology. Here's the problem. When we measure how fast the universe is expanding using nearby stars and supernova, we get one number. But when we calculate it using the afterglow of the Big Bang, the cosmic microwave background, we get another. And these numbers don't just disagree slightly, they clash by enough to keep astronomers awake at night, with the gap stubbornly widening as our instruments grow sharper. At first, researchers dismissed the mismatch as a simple calibration error. Maybe our telescopes weren't aligned perfectly, or perhaps there was dust skewing the measurements. But as years passed and technology improved, the discrepancy refused to vanish. If anything, it deepened, like a crack in a windshield spreading with each new observation. The unsettling truth, our two most trusted methods for measuring cosmic expansion, the very yardsticks we've used to map the universe's history, might be telling us two different stories about reality itself. One explanation points to dark energy, the mysterious force accelerating the universe's expansion. What if dark energy isn't constant, as we've assumed? What if it's growing stronger over time or interacting with matter in ways we haven't accounted for? This could mean the universe's expansion rate isn't just speeding up, it's doing so unevenly, creating the illusion of a discrepancy when we compare local measurements to ancient light from the Big Bang. Then there's the radical possibility that our cosmic yardstick is broken. The cosmic microwave background relies on a bedrock assumption that the early universe was smooth and uniform, its tiny fluctuations predictable. But what if there's hidden structure, wrinkles in space-time we haven't detected? Some theorists speculate that our corner of the cosmos might sit inside a vast underdense region, a cosmic bubble where gravity's pull is weaker than average, skewing our local measurements. Imagine measuring the speed of a river while standing in an eddy. You'd get a distorted picture of the current's true force, the most tantalizing and unsettling theory. We might be seeing the first hints of new physics, forces or particles beyond the standard model that subtly reshape how the universe expands. Certain quantum gravity models predict extra dimensions or exotic fields that could tweak gravity's strength on cosmic scales, just enough to explain the tension. It's as if the universe is whispering, your equations are missing a term. What makes this more than an academic debate is the sheer weight of evidence piling up on both sides. Teams using the Hubble Space Telescope to track pulsating stars get one expansion rate. Those mapping the cosmic microwave background with Planck satellite data get another. Both methods are meticulous, both peer-reviewed, both seemingly flawless, yet they refuse to agree. The tension isn't fading with better data, it's hardening into a paradox. And here's the humbling part, we've been here before. In the 1920s, when Edwin Hubble first discovered the universe was expanding, his initial measurements were off by a factor of 7. The error wasn't in the science but in the tools. Could history be repeating itself, or are we staring at the edges of a revolution where the cracks in our models reveal deeper truths hidden beneath? The Hubble tension isn't just a problem to solve. It's an invitation to question, to explore, to admit that after centuries of cosmic cartography, the universe might still be holding its greatest cards close. Whether the answer lies in recalibrated instruments or rewritten physics, one thing's certain, the cosmos is daring us to look closer, because sometimes the most profound discoveries begin not with a eureka, but with a stubborn, inconvenient discrepancy that refuses to go away. Quantum entanglement already shatters our everyday intuition, particles separated by light years influencing each other instantly, as if space doesn't exist between them. But what if that's only half the story? What if these ghostly connections don't just thread through space, but weave through time itself? Imagine flipping a coin in your backyard today, only to realize its outcome was determined by something you'll do next week. It sounds like paradox fodder, the kind of idea physicists once laughed out of the room. Yet in labs around the world, experiments are revealing something astonishing. Entanglement might not care which way time flows. The first clues emerged from delayed choice experiments, those mind-bending tests where a particle's behavior seems to change based on measurements made after it's already been detected. In one landmark study, scientists split photons through a beam splitter, allowing them to take two paths. When they measured which path a photon took, it behaved like a particle. But if they erased that information after the fact retroactively from the photon's perspective, it suddenly acted like a wave, as if the future measurement rewrote history. The implications are staggering. Causality, that bedrock principle that causes precede effects, starts to look like a suggestion rather than a law. Now, researchers are pushing further. By entangling particles and then manipulating one of them after the other has already been measured, they've found correlations that only make sense if influence travels backward through time. Think of it like sending a text message to the past, except instead of words, you're sending quantum states. In 2021, a team in Vienna demonstrated this by entangling photons and then altering the measurement basis of one photon based on the outcome of its partner, which had already been recorded. The result, the first photon's behavior shifted to match, as if it knew what its future twin would decide. The wildest twist comes from cosmic scale entanglement. Some theories suggest particles created during the Big Bang might still be entangled today, their quantum states linked across 13.8 billion years. If that's true, measuring one could instantaneously affect its partner's state in the distant past, not through some sci-fi time machine, but through the universe's built-in quantum wiring. It's as if time, at its most fundamental level, isn't the one-way street we experience, but a vast, interconnected web where past and future constantly whisper to each other. Of course, this doesn't mean you can change history or erase your mistakes. Quantum effects are subtle, playing out in the subatomic realm where probabilities reign. But it does force us to confront a radical possibility, that the universe's deepest laws might not distinguish between past and future at all. Entanglement could be the thread stitching the cosmos together, not just across space, but across time itself, a silent, invisible network where every moment is somehow present in every other. The most humbling part, we almost dismissed this as mathematical fantasy. Einstein himself called entanglement spooky action at a distance, never imagining it might also be spooky action across time. Now, as experiments peel back layer after layer of this mystery, we're left with a chilling yet thrilling thought. The universe's greatest secrets might not lie ahead of us or behind us, but in the quantum shadows where both directions blur into one. Pluto's heart shouldn't be alive. That vast, icy plain stretching over 1,000 kilometers across its surface, dubbed Tombaugh Regio after the dwarf planet's discoverer, was supposed to be a frozen graveyard, a relic of impacts from the solar system's chaotic youth. When New Horizons raced past Pluto in 2015, scientists expected to find a barren, cratered world, its geology long since frozen in time. Instead, the probe captured something astonishing, a landscape pulsing with activity. Glaciers of nitrogen ice creep like slow-motion rivers. Mountains of water ice rise taller than the Rockies, their peaks dusted with exotic snowfalls of methane. And at the heart of it all, literal and metaphorical, lies Sputnik Planitia, that iconic heart-shaped basin defying every prediction with its eerie, dynamic youth. The mystery starts with the ice. Pluto's surface hovers just 38 degrees above absolute zero, cold enough to turn gases like nitrogen and methane into solids as hard as rock. Yet New Horizons spotted nitrogen glaciers flowing into Sputnik Planitia, their movement betraying the presence of a slushy, semi-liquid layer beneath. Even stranger, the basin's center is conspicuously devoid of craters, suggesting something is constantly erasing them, resurfacing the area in a process that, by all rights, should have ended billions of years ago. The leading theory, a hidden ocean of liquid water, insulated by layers of exotic ices and kept warm by radioactive decay in Pluto's rocky core, might be bubbling up to reshape the surface. Imagine a snow globe half filled with antifreeze, shaken by forces we're only beginning to understand. Then there are the cryovolcanoes. Near the heart's western edge, New Horizons spotted two massive mounds, Wright Mons and Pickard Mons, rising over 4 kilometers high with deep central pits. Unlike Earth's fiery volcanoes, these would erupt slurries of icy slush, spewing frozen nitrogen, ammonia, or water mixed with organic compounds, the kicker. Some of these features appear freshly active, their flanks unmarred by the cosmic sandblasting of micrometeorites. It's as if Pluto's interior is coughing up its secrets, one frosty belch at a time. But the real jaw-dropper is the heart's gravitational pull. Sputnik Planitia isn't just a surface feature, it's a cosmic anchor. The basin's mass is so significant that it's locked Pluto's rotation, forcing the dwarf planet to always keep its heart facing its largest moon, Charon, in a gravitational embrace. Computer simulations suggest this alignment isn't accidental. The basin might be an ancient impact scar that later filled with ice, its weight acting like a thumb on the scales of Pluto's spin. Yet even this explanation feels incomplete. Why hasn't the ice sunk deeper over time? What keeps it mobile enough to reshape the surface? The answer might lie in convection. Like a pot of boiling water, Pluto's icy heart could be churning, with warmer material rising from below while colder ice sinks. This slow-motion dance would explain the glacier flows and the lack of craters, but it requires a heat source far beyond what traditional models predict. Some researchers speculate that Pluto's core might still hold pockets of radioactive elements like potassium-40, their decay generating just enough warmth to keep the engine running. Others propose that the nitrogen ice itself acts as a thermal blanket, trapping heat through some exotic phase change we've yet to replicate in labs. What's haunting isn't just the science, it's how close we came to writing Pluto off. For decades, astronomers assumed small, distant worlds like this were inert balls of rock and ice, their stories long since concluded. New Horizons didn't just overturn that assumption. It revealed a world where geology and chemistry conspire to keep the lights on against all odds. Pluto's heart isn't a frozen artifact. It's a clockwork marvel ticking quietly in the dark, reminding us that even the solar system's quietest corners can hold surprises hot enough to melt our expectations. Mars methane spikes are the solar system's most frustrating game of hide and seek. One moment, a rover's sensors pick up a faint whiff of the gas, just enough to make scientists sit bolt upright. The next, it's gone, vanishing into the thin Martian air before follow-up tests can confirm it. These fleeting detections have haunted researchers for nearly 2 decades, ever since the European Space Agency's Mars Express orbiter first spotted methane's spectral fingerprint in 2004. At first, the scientific community dismissed them as ghosts in the machine, electronic hiccups, or contamination from the rovers themselves. But then Curiosity's tunable laser spectrometer began catching the same whispers, its ultra-precise measurements leaving no doubt something on Mars is belching methane, and it's doing so on a schedule we can't predict. The mystery isn't just the methane's presence, it's the way it behaves. On Earth, methane lingers in the atmosphere for centuries, mixing uniformly across the globe. But on Mars, it appears in sudden, localized bursts, sometimes spiking to 40 times background levels before dissipating within weeks. This isn't just odd. It's impossible under known atmospheric chemistry. The Martian air should destroy methane in about 300 years, yet these spikes suggest something is replenishing it far faster than geology alone can explain. That's where biology enters the picture. 90% of Earth's methane comes from living organisms, cows, rice paddies, microbes buried deep underground. Could Mars' sporadic plumes be the exhaust of some subsurface microbial ecosystem, thriving in briny aquifers beneath the rust-colored soil? Recent lab experiments show certain Earth bacteria can survive Mars-like conditions, metabolizing hydrogen and carbon dioxide into methane even in freezing, radiation-blasted environments. If similar microbes exist in Mars' damp subsurface layers, their metabolic byproducts could seep through cracks and vents, creating the very spikes we're detecting. Yet the plot thickens. In 2019, the European-Russian trace gas orbiter designed specifically to sniff Martian methane found none at all, not a trace. This contradiction isn't just puzzling, it's maddening. How can Curiosity measure plumes while orbiters overhead see nothing? One theory suggests the methane is being destroyed near the surface by some unknown chemical process, perhaps involving Martian dust or solar radiation. Another posits that the gas is being released in such narrow, localized vents that orbiters simply miss the plumes, like satellites failing to spot a single smoking chimney on Earth. The most tantalizing clue comes from the timing. Some of Curiosity's methane spikes coincide with Martian summer, when subsurface temperatures might warm just enough to melt permafrost and release trapped gases. Others follow seasonal dust storms, which could shake loose methane from underground reservoirs or even expose fresh vents. It's a pattern that feels almost biological. On Earth, methane emissions spike during warm, wet seasons when microbial activity peaks. Is Mars playing by the same rules? Of course, non-biological explanations still hold weight. Serpentinization, a chemical reaction between water, carbon dioxide, and certain minerals, can produce methane abiotically. Mars' ancient volcanic regions might still harbor pockets of geothermal activity, slowly cooking methane deep underground. There's even a chance the gas is being delivered by micrometeorites, which carry organic compounds that break down into methane when they hit the planet's surface. But none of these explain the spike's erratic behavior. Geology is predictable, life not so much. What makes this mystery so gripping isn't just the question of life. It's the way Mars seems to be toying with us, dangling clues just out of reach. Every time we think we've pinned down the methane source, it slips away, like a cosmic magician's trick where the answer is always in the next data set, the next mission, the next rover. The real lesson here might not be about methane at all, but about humility. For all our advanced instruments and orbital eyes in the sky, Mars still keeps its secrets close. Whether the answer is microbes, minerals, or something we haven't even imagined yet, one thing's certain: the red planet isn't done surprising us. Dark energy was supposed to be the universe's steady hand, an unchanging force gently pushing galaxies apart at an ever-increasing rate. But what if we've been wrong? What if this mysterious driver of cosmic expansion isn't constant at all? Hidden in the light of distant supernova, Astronomers are spotting anomalies that suggest dark energy might be growing stronger or weaker or even flickering unpredictably across billions of years. This isn't just academic curiosity. The fate of everything, stars, planets, even spacetime itself, could hinge on this one overlooked detail. The first hints emerged from Type Ia supernova, the same celestial beacons that revealed cosmic acceleration in the 1990s. These dying stars explode with such predictable brightness that astronomers use them as cosmic yardsticks to measure vast distances. But when researchers compared supernovae from different cosmic eras, some relatively young, some ancient, they noticed something odd. The older explosions appeared slightly dimmer than expected, as if dark energy's push had been weaker in the early universe. At first, scientists chalked it up to measurement errors or interstellar dust. But as more data poured in from observatories like the Dark Energy Survey and Pan-STARRS, the pattern held. The numbers refused to line up unless dark energy itself was changing over time. Here's where it gets existential. If dark energy strengthens as the universe expands, a scenario theorists call phantom energy, it could eventually shred reality itself. Picture a rubber band stretched tighter and tighter until it snaps. In this nightmare scenario known as the Big Rip, galaxies would first tear apart, then stars, then planets, and finally atoms, all torn asunder by dark energy's runaway dominance. But if dark energy weakens, the cosmos might face a slower, colder fate. Heat death, where expansion continues but at a crawl, leaving the universe a vast, dark graveyard of exhausted stars and black holes. The wild card, dark energy, might not be a single force at all. Some models propose it's the collective effect of multiple quantum fields flickering in and out of existence, their combined influence waxing and waning like tides. Others suggest it's tied to the vacuum energy of space itself, a cosmic battery slowly draining as the universe ages. The most radical idea, dark energy could be interacting with dark matter, an unseen handshake between the universe's two greatest mysteries, subtly altering how they shape cosmic destiny. What's terrifying isn't just the scale of these possibilities, it's how easily we might have missed them. For decades, cosmologists treated dark energy as a fixed constant, a simple term in Einstein's equations. Only now, with telescopes peering deeper into space and further back in time, are we catching whispers of its true nature. The James Webb Space Telescope could be the game changer, its infrared eyes scanning the earliest supernova for clues about dark energy's youth. Will it reveal a force fading with age or one gathering strength like a storm? The irony is profound. We've mapped the cosmic microwave background, traced the large-scale structure of galaxies, even detected gravitational waves, yet this invisible driver of everything remains as enigmatic as ever. Dark energy's potential mutability isn't just a puzzle. It's a mirror held up to our assumptions, revealing how much we still don't understand about the fabric of reality. One day, we might look back at our current models the way we now view the static, eternal universe of the 19th century, a quaint oversimplification of forces far stranger and more dynamic than we dared to imagine. Until then, every flicker in the data, every anomalous supernova, is a breadcrumb on the path to answers, or perhaps to questions we haven't even thought to ask yet. The universe hums with electromagnetic noise, a cacophony of pulsars, quasars, and the faint afterglow of the Big Bang. Yet amid this cosmic static, one frequency remains conspicuously absent: the deliberate broadcasts of alien civilizations. This eerie silence gnaws at the heart of the Fermi paradox, the unsettling disconnect between the universe's vast potential for life and our total lack of evidence for it. But what if the silence isn't an accident? What if it's a survival strategy woven into the fabric of intelligent life itself? recent theories suggest a chilling possibility. Advanced civilizations might be hiding. Not out of shyness but necessity, imagine a universe where technological species inevitably encounter predatory rivals, where broadcasting your location is akin to lighting a signal fire in a forest teeming with wolves. This grim logic, known as the dark forest hypothesis, paints a cosmos where every civilization stays quiet to avoid annihilation. Any species reckless enough to announce its presence would be swiftly eliminated by older, more advanced predators lurking in the shadows. It's a galactic game of hide and seek where the penalty for being found is extinction. There's precedent for this kind of caution right here on Earth. During the Cold War, nuclear submarines operated under strict radio silence to avoid detection. Even today, militaries use stealth technology to disappear from radar. If humanity instinctively grasps the value of invisibility in a hostile environment, why wouldn't extraterrestrials? The universe is billions of years older than Earth, plenty of time for countless civilizations to rise, make the fatal mistake of broadcasting their existence, and vanish. The survivors would be the ones who learn to cloak their presence, their signals deliberately indistinguishable from background noise. This raises an unsettling corollary. We might already have detected alien transmissions without realizing it. Modern astronomy filters out noise to focus on celestial signals, automatically discarding anything resembling artificial patterns. In 2017, the Breakthrough Listen project identified a strange radio burst from Proxima Centauri that matched the profile of an artificial signal. Later analysis dismissed it as terrestrial interference, but what if we're too quick to label anomalies as glitches? Our algorithms could be scrubbing the very evidence we seek from the data, like archivists unknowingly burning priceless manuscripts while tidying their shelves. Even more provocative is the idea that ancient alien signals might be hiding in plain sight. The WOW signal, that infamous 72-second burst detected in 1977, remains unexplained. Some researchers argue its frequency and duration align suspiciously well with what an interstellar beacon might look like. Yet without repetition, it's been relegated to cosmic folklore. Similarly, fast radio bursts, those intense, milliseconds-long pulses from deep space, exhibit patterns that defy natural explanations. Could these be fragmented transmissions from civilizations that long ago retreated into silence, their messages now drifting like bottles in a galactic ocean? The dark forest isn't the only answer, of course. Another possibility is that advanced civilizations transcend radio altogether, communicating via quantum entanglement or other physics we've yet to discover. Imagine ants trying to comprehend the internet by listening to soil vibrations. That might be our predicament. Or perhaps they're observing us quietly, adhering to a cosmic version of the Prime Directive, unwilling to interfere until we reach a certain technological threshold. But the most haunting scenario is one where we're truly alone, where the silence isn't a choice but a verdict. Either way, the Fermi paradox forces us to confront not just the mystery of alien life, but the fragility of our own. In a universe where survival might require perpetual silence, every signal we send carries risk. Are we the naive newcomers shouting into the void, unaware of the predators listening? Or is the darkness empty after all, leaving us as the sole flicker of consciousness in an indifferent cosmos? The answer, like the universe itself, remains shrouded in quiet. The solar system isn't quite the orderly clockwork model we once imagined. If you could view it from the side, you'd notice something odd. The planets don't orbit in perfect alignment with the sun's equator. Instead, the entire planetary disk tilts at about 6 degrees, as if some unseen hand knocked our cosmic neighborhood askew. For years, astronomers blamed this slant on ancient chaos, violent collisions during the solar system's infancy that sent planets reeling. But new simulations suggest a far more dramatic culprit, a passing star long vanished whose gravity may have yanked our planetary cradle off kilter like a cosmic billiard ball. Picture the early solar system, just a few million years old, a swirling disk of gas and dust where planets were beginning to coalesce. Suddenly, a rogue star drifts dangerously close, perhaps within a few hundred astronomical units. Its gravitational pull tugs at the protoplanetary disk, warping its shape. Computer models show that even a brief encounter lasting mere decades could impart enough torque to explain the tilt we see today. The math is compelling. A star roughly the Sun's mass, passing at the right angle and distance, matches the observed misalignment almost perfectly. What makes this theory so electrifying is its implications for our cosmic history. If true, it means our solar system wasn't always this isolated island. In its youth, the Sun likely shared space with thousands of sibling stars in a dense stellar nursery where close encounters were common. Most have since drifted apart, scattered by galactic tides, but their gravitational handshakes may have left permanent scars. Some researchers speculate this stellar visitor could even explain other solar system oddities, like the hypothetical planet Nine's peculiar orbit or the Kuiper belt's warped edges. The real twist: we might have already found the culprit. Astronomers recently identified HD 1626, a star currently speeding away from us at breakneck velocity. Tracing its motion backward, simulations suggest it passed within a light year of the Sun around 3 million years ago, just when the solar system's architecture was still malleable. While it's too distant to have caused the tilt itself, its existence proves such close encounters aren't just theoretical. Other candidates, now lost to time, could have come even closer. Yet not everyone's convinced. Critics point out that a passing star would likely disrupt more than just the orbital plane. It could fling planets into erratic orbits or eject them entirely. Alternative explanations, like gravitational imbalances within the protoplanetary disk itself, might explain the tilt without invoking interstellar trespassers. Then there's the lingering mystery of Jupiter's role. As the solar system's heaviest planet, its migrations during the early chaos could have torqued the entire disk like a spinning top losing balance. Perhaps the most tantalizing clue lies in exoplanetary systems. Observations of young stars elsewhere in the galaxy frequently show misaligned disks, many with tilts far more extreme than ours. Some even host planets orbiting perpendicular to their stars spin, a smoking gun for past gravitational disturbances. If our solar system's modest slant seems unremarkable in this context, it might be the rule rather than the exception, a universal signature of stellar neighborhood dynamics. What's humbling isn't just the idea that a long-lost star might have knocked us off kilter. It's the realization that our cosmic address wasn't always this quiet. The same gravitational ballet that gave us our tilt could have also delivered water-rich comets or nudged asteroids into Earth's path, events that may have shaped life's very origins. The solar system's slight wobble isn't just a curiosity. It's a fossil, a silent witness to the tempestuous stellar nursery we once called home. And if we're reading its clues right, it's proof that even the grandest cosmic architectures bear the fingerprints of ancient, fleeting encounters, moments when the universe reached out and left its mark. Exoplanets were supposed to follow the rules, neat, circular orbits around their stars, all moving in the same direction like a well-rehearsed cosmic ballet. Then we found the rebels. Take WASP 17b, a gas giant soaring backward around its star, defying every model of planetary formation. or the rogue planets drifting through interstellar space without a sun to call home, untethered and alone. At first, astronomers dismissed these oddballs as statistical noise, glitches in the data, artifacts of imperfect detection methods. But as our catalogue of alien worlds grew, so did the roster of rule breakers, until one thing became undeniable: the universe has a flair for planetary anarchy. The backward orbits, known as retrograde motion, shouldn't exist under traditional theories. Planets form from spinning disks of gas and dust, inheriting their star's rotation like children mimicking a parent's dance. For a world to flip its orbit, something catastrophic must have intervened. A gravitational tug of war with a passing star, perhaps, or a violent collision that sent the planet careening off course. Some systems, like Kepler-56, host multiple planets tilted at bizarre angles, their orbits crisscrossing like spaghetti strands tossed onto a table. These aren't accidents. They're scars from cosmic brawls, evidence of planetary systems that survived their own turbulent adolescences. Then there are the loners' rogue planets ejected from their birthplaces, cast adrift in the eternal night between stars. Infrared telescopes have spotted these nomads glowing faintly with residual heat, their surfaces frozen wastelands where the only sunlight comes from distant galaxies. Theorists once assumed such ejections were rare, the result of freak gravitational encounters, but simulations now suggest that in crowded young star clusters, planets might be flung into the void as routinely as pebbles kicked up by a passing car. Some could even outnumber stars in our galaxy, a hidden population of dark wanderers mapping invisible highways through the cosmos. The most tantalizing outliers, though, are the stolen worlds. In binary star systems, astronomers have spotted planets orbiting one star at extreme distances, their paths too wide and unstable to have formed there naturally. The likely explanation: these planets were snatched from the other star during a close encounter, a celestial game of gravitational keep away. Picture two siblings fighting over a toy, except the siblings are stars and the toy is a Jupiter-sized world ripped from one orbit and hurled into another. The chaos doesn't stop there. Some models suggest our own solar system might have hijacked a planet or two in its youth, with distant objects like Sedna potentially being captured interstellar interlopers. What's humbling isn't just the diversity of exoplanets, it's how long we resisted seeing it. Early detection methods favored orderly, close-in worlds, biasing our view toward well-behaved systems. The outliers were there all along, lurking in the margins of datasets, waiting for someone to take them seriously. Now, as telescopes like JWST and TESS peer deeper into the cosmic menagerie, we're finding that the exceptions might be the rule. The universe doesn't just tolerate planetary chaos, it revels in it, crafting systems where the only constant is unpredictability. And that's the real lesson here. Every time we think we've pinned down the rules of planet formation, the cosmos throws us a curveball. Maybe backward orbits and rogue worlds aren't glitches. Maybe they're the universe's way of reminding us that gravity, for all its mathematical elegance, is a force of infinite creativity, one that sculpts not just orderly clockwork systems, but wild, untamed galaxies where planets dance to rhythms we're only beginning to hear. The next time you look up at the night sky, remember, out there somewhere, a world is breaking all the rules, and that's exactly how it's supposed to be. Jupiter's atmosphere was supposed to be dripping with water. When NASA Galileo probe plunged into the gas giant's swirling clouds in 1995, scientists eagerly awaited the data, expecting to confirm long-held theories about Jupiter's composition. The planet's hydrogen-rich environment, they reasoned, should have locked away vast amounts of oxygen in the form of water, 3 times more than the Sun holds by some estimates. But the numbers didn't add up. the probe detected barely a tenth of the expected water, leaving researchers scratching their heads. At first, they blamed the instruments. Maybe the probe had plunged through an unusually dry patch, a cosmic desert in Jupiter's otherwise soggy skies. Or perhaps the sensitive equipment had failed to vaporize and measure water trapped in ice crystals. But when the Juno spacecraft arrived decades later with more advanced sensors, the mystery deepened. Jupiter wasn't just drier than predicted, it was parched in ways that defied every model of planetary formation. The answer might lie beneath the clouds. Jupiter's atmosphere isn't a uniform soup of gases. It's a layered onion of storms and currents, with materials segregating by density and temperature. Water heavier than hydrogen and helium could be sinking toward the planet's core, dragged down by colossal weather systems like a teaspoon of honey sinking through tea. Some models suggest vast waterbergs, slushy, continent-sized masses of ice and water vapor, might be drifting far below the visible cloud decks, sequestered in regions our probes can't yet reach. It's as if Jupiter swallowed its oceans whole, hiding them behind a veil of ammonia and hydrogen sulfide. Then there's the diamond rain. At extreme pressures and temperatures deep inside Jupiter, carbon atoms ripped from methane molecules could crystallize into diamonds, falling like glittering hail through layers of metallic hydrogen. This surreal phenomenon, once dismissed as science fiction, gained traction when lab experiments recreated similar conditions on Earth, producing nanodiamonds from hydrocarbon mixtures. If Jupiter's interior truly hosts these gemstone showers, they might act like sponges, soaking up oxygen atoms that would otherwise bond with hydrogen to form water. The result, a planet that's not just hiding its water, but actively transforming it into something far more exotic. The implications stretch beyond Jupiter. If water isn't evenly distributed in the solar system's largest planet, our understanding of how planets form and where life might emerge could need a rewrite. Gas giants like Jupiter are thought to be cosmic vacuum cleaners, their gravity scooping up water-rich comets and asteroids during their infancy. If that water isn't in the atmosphere, where did it go? Is it trapped in Jupiter's depths, or was it never there to begin with? Some theorists propose Jupiter might have formed closer to the Sun, in a hotter region where water vapor was scarce before migrating outward. Others speculate that our measurements are fine. We're just looking in the wrong places, like trying to gauge Earth's oceans by sampling the Sahara. The most tantalizing clue comes from Juno's microwave radiometer, which peers deeper into Jupiter's atmosphere than any instrument before it. Recent data reveals pockets of elevated water concentrations near the equator, hinting at a planet-wide imbalance. Perhaps Jupiter's water isn't missing. It's just playing hide and seek, pooling in turbulent cyclones or cascading into the abyss in diamond-laden waterfalls we can't yet see. Every new observation peels back another layer of this enigma, revealing a world far stranger than the textbook diagrams of a bland, banded gas giant. What's humbling isn't just the mystery of Jupiter's dry spells, it's how quickly we assumed we knew the rules. For decades, planetary science treated gas giants as predictable constructs: hydrogen, helium, and a dash of water stirred by rotation. But Jupiter laughs at our simplicity. Its missing water isn't an error in the data. It's a challenge, a cosmic riddle scrawled across the solar system's largest canvas, daring us to look deeper. Because if there's one thing Jupiter teaches us, it's that the universe's most dazzling secrets often lurk where we least expect them, not in the light but in the shadows. The Great Attractor lurks in the cosmic shadows like a gravitational siren, pulling our entire galaxy along with hundreds of thousands of others toward it at over 600 kilometers per second. For decades, astronomers puzzled over this mysterious force. their telescopes thwarted by the thick dust clouds of the Milky Way's own disk, which obscured the view toward the constellation Centaurus. Early attempts to map the culprit revealed only fragments, a loose gathering of galaxies called the Norma cluster, its gravity far too feeble to explain the violent tug we felt. It was like hearing the roar of a waterfall but seeing only a trickle of water. The math insisted something enormous was out there, yet every observation came up short until we learned to see through the dust. Infrared telescopes changed everything. By piercing the veil of interstellar debris, they unveiled the true scale of our captor, not just a cluster, but a sprawling supercluster of galaxies, 100 quadrillion times the mass of our Sun, anchored by a dense knot of dark matter. This is Laniakea, our galactic home on the grandest scale, a filamentary web stretching over 500 million light-years where galaxies flow like rivers toward the Great Attractor's gravitational basin. But here's the twist, even this behemoth might be a waypoint. The attractor itself seems to be in motion, dragged toward something even larger and more distant lurking beyond the observable horizon. What could exert such a pull? One theory points to the Shapley supercluster, a staggering assembly of galaxies 3 times more massive than Laniakea, lying another 600 million light-years farther on. Others speculate about the Vela supercluster, a recently discovered structure so vast it warps the cosmic microwave background. But the most tantalizing possibility is that we're glimpsing the edge of something fundamental, a flaw in the universe's fabric where inflation stretched space-time unevenly during the Big Bang, leaving behind a gravitational scar that still tugs at everything in its reach. The irony is delicious. For centuries, humanity placed itself at the center of creation. Now, we find ourselves not just adrift in a cosmic backwater, but caught in a riptide of dark matter and galaxies, swept toward an unseen leviathan whose full nature might forever elude us. The Great Attractor isn't just a destination. It's a signpost hinting at structures so colossal they redefine our understanding of the cosmos. And as our telescopes peer deeper, one truth becomes clear. The universe's greatest mysteries aren't just hidden in darkness. They're pulling us toward them. Venus was supposed to be a textbook example of a dead world, a scorching, sulfurous hellscape where nothing could survive. Then came the Phosphine. In 2020, astronomers announced they'd detected this noxious gas in Venus's upper clouds, sparking a firestorm of controversy. On Earth, phosphine is almost exclusively produced by microbes thriving in oxygen-free environments like swamps and animal guts. Finding it floating 50 kilometers above Venus's surface was like stumbling upon a smoke signal in a desert long thought abandoned. The implications were staggering. Could acidic cloud droplets in Venus's temperate, habitable zone harbor microbial life, floating like cosmic plankton in a global aerial ocean? Skeptics pounced immediately. Maybe the signal was a fluke, an artifact of telescopic interference or faulty data processing. Perhaps volcanic activity or exotic chemistry could explain the phosphine without invoking biology. But subsequent observations only deepened the mystery. Independent teams confirmed the detection, though at lower concentrations, while others found nothing at all. The scientific community found itself at an impasse, divided between those seeing whispers of life and those dismissing it as wishful thinking. Here's what makes this debate so electrifying. Venus's cloud decks hover at a balmy 30 degrees Celsius with pressures similar to Earth's surface, a far cry from the crushing, lead-melting inferno below. These clouds are also rich in sulfur compounds, which certain extremophile microbes on Earth use as energy sources. Picture a hypothetical aerial ecosystem, microbes encased in droplet balloons, metabolizing sulfur and exhaling phosphine as they drift through Venus's perpetual twilight. It's a scenario straight out of science fiction, except the data refuses to let us rule it out. Yet Venus isn't making this easy. The planet's thick atmosphere absorbs phosphine's telltale spectral signature, forcing astronomers to tease faint signals from overwhelming noise. Some researchers argue the original detection might have confused sulfur dioxide, a common Venusian gas for phosphine. Others counter that newer analyses, including data from the James Webb Space Telescope, still show unexplained spectral lines right where phosphine should appear. The conflicting results feel less like a scientific dead end and more like a cosmic shell game where the truth keeps shifting just out of focus. The most tantalizing clue lies in the phosphine's persistence. If non-biological processes like lightning or meteor strikes were producing it, the gas should vanish quickly under Venus's intense ultraviolet radiation. Yet the signal lingers, suggesting an ongoing source, a factory constantly replenishing what the atmosphere destroys. On Earth, that factory is life. On Venus, it could be geology we don't yet understand, or something far more extraordinary. What's haunting isn't just the possibility of life next door, it's how close we came to missing it entirely. For decades, Venus was written off as a cautionary tale of runaway greenhouse effects, its clouds dismissed as sterile droplets of sulfuric acid. Now, those very clouds might be hiding the most profound discovery in astrobiology, if we're brave enough to take the data seriously. Upcoming missions like NASA Da Vinci and ESA's Envision aim to probe Venus's atmosphere directly, hunting for phosphine and other potential biosignatures. Until then, the planet hangs in our sky like a riddle wrapped in toxic vapor, a world we thought we knew, suddenly brimming with forbidden questions. Neptune's poles should be the coldest places on the planet. After all, this is an ice giant, a world so distant from the sun that sunlight there is barely stronger than moonlight on Earth. Yet when Voyager 2 raced past Neptune in 1989, its instruments picked up something bizarre. The planet's south pole was significantly warmer than the equator, glowing with an unexpected infrared heat. At the time, scientists dismissed the anomaly as sensor noise or an artifact of the probe's hasty flyby. The images were grainy, the data incomplete. Surely this couldn't be real. But decades later, when modern telescopes like Keck and Oumuamua turned their gaze toward Neptune, they found the same impossible heat signature, this time with even more unsettling details. The poles weren't just warm, they were simmering. Neptune's south pole clocked in at about 10 degrees Celsius hotter than the rest of the planet, a staggering difference for a world where average temperatures hover around -200 degrees. Even stranger, the heat wasn't evenly distributed. It concentrated in a swirling vortex of storms, a churning maelstrom of methane and hydrogen with winds screaming at over 1,000 kilometers per hour. For an ice giant, this was like finding a roaring bonfire at the center of a glacier. So what's fueling Neptune's polar furnace? One leading theory points to atmospheric dynamics gone wild. Unlike Earth, where sunlight drives weather, Neptune's heat comes almost entirely from within leftover energy from its formation, slowly leaking out. Normally, this heat escapes evenly across the planet's surface, but something about Neptune's poles disrupts the balance, acting like a pressure valve for the planet's internal furnace. Computer simulations suggest that as gases spiral toward the poles, they compress and heat up like air rushing into a bicycle pump. The extreme winds then trap this warmth, creating a self-sustaining feedback loop where hot air can't escape, only grow hotter. But here's the twist: Neptune's poles aren't always hot. Observations reveal the warmth shifts over time, fading at one pole only to flare up at the other. This bizarre flip-flop hints at something deeper at work, perhaps a seasonal cycle, but on a scale we've never seen. Neptune takes 165 Earth years to orbit the Sun, meaning each season lasts over 40 years. The slow creep of sunlight, weak as it is, might be enough to tip the balance in the planet's atmosphere, triggering decades-long heating and cooling cycles at the poles. The most tantalizing possibility, though, involves Neptune's magnetic field. Unlike Earth's relatively orderly magnetosphere, Neptune's field is a chaotic mess, tilted at 47 degrees and offset from the planet's core. Charged particles streaming along these skewed magnetic lines could be funneled toward the poles, smashing into the atmosphere like a cosmic particle accelerator and dumping heat where they collide. If true, it would mean Neptune's poles aren't just warm, they're the endpoints of an invisible, interplanetary circuit we're only beginning to map. What's humbling isn't just the mystery of Neptune's hot poles. It's how long we overlooked them. For years, Voyager's fuzzy data was filed away as a curiosity, a glitch to be explained later. Now, as sharper telescopes unveil the truth, we're left grappling with a planet that refuses to play by the rules. Neptune was supposed to be a quiet, frozen sentinel at the solar system's edge. Instead, it's a dynamic, storm-racked enigma, proof that even the coldest corners of the cosmos can hide the most unexpected fires. And if we've learned anything from this ice giant's secrets, it's that the universe's most thrilling discoveries often start with a flicker of heat in the dark. Galactic superbubbles are the universe's silent architects, gaping voids in space so immense they could swallow entire solar systems, yet invisible to the naked eye. These colossal cavities, some spanning thousands of light years, were long dismissed as cosmic dead zones, the aftermath of ancient stellar explosions that had long since faded into darkness. But the truth is far more electrifying. These so-called empty regions are anything but quiet. They're particle accelerators on a galactic scale, factories churning out high-energy cosmic rays that zip through the universe at nearly the speed of light. And they've been shaping our galaxy's destiny for billions of years, hidden in plain sight. The story begins with massive stars, those brilliant behemoths that live fast and die young. When these stars reach the end of their lives, they don't fade quietly. They explode as supernova, unleashing shockwaves so powerful they carve vast bubbles into the interstellar medium. Multiply that across generations of stars clustered together, and you get a superbubble, a growing cavity where successive supernova pile on like dynamite, blasts in a single quarry, heaving gas and dust outward until all that's left is a hollow shell of turbulent energy. For decades, astronomers assumed these regions were little more than fossilized remnants, their work done. Then came the cosmic rays, high-energy particles, protons, electrons, even atomic nuclei, rained down on Earth from space, some with energies millions of times greater than anything produced in our most powerful particle colliders. Where do they come from? The answer, it turns out, might be these superbubbles. As shockwaves from supernova ripple through the cavities, they act like natural particle accelerators, surfing charged particles on magnetic fields until they reach mind-bending velocities. Imagine a pinball machine the size of a galaxy, where particles ricochet off shock fronts, gaining speed with every collision until they're ejected into the cosmos like bullets from a barrel. But here's the twist: these bubbles aren't just chaotic maelstroms, they're surprisingly organized. Observations of regions like the local bubble, a cavity surrounding our solar system, reveal intricate filamentary structures woven into the bubble's walls, where magnetic fields coil like springs under unimaginable tension. These filaments might be the key to the acceleration process, acting as cosmic slingshots that fling particles outward with pinpoint precision. It's a level of fine-tuning that challenges our understanding of how energy dissipates in space, suggesting these voids are more like finely engineered machines than the aftermath of random explosions. The implications ripple across astronomy. Superbubbles could explain why certain regions of the galaxy seem to spawn stars at breakneck speeds, their shockwaves compressing nearby gas clouds until they collapse into new suns. They might also hold clues to one of the universe's greatest mysteries, the origin of cosmic rays, those enigmatic particles that have baffled scientists since their discovery over a century ago. Some researchers even speculate that life on Earth owes its existence to these bubbles. Their turbulent winds might have delivered the heavy elements essential for life, or triggered the formation of our solar system in a fertile pocket of space. What's most humbling, though, is how long we underestimated these structures. For years, superbubbles were cartographic curiosities, blank spots on the galactic map to be filled in later. Now we're realizing they're active players in the cosmos, shaping everything from star formation to the very particles that streak through our atmosphere. Their silence wasn't emptiness, it was the quiet hum of a machine too vast for us to hear. And as telescopes peer deeper into these voids, we're left with a thrilling thought: the universe's grandest engines might not roar. They whisper. The Kuiper belt was supposed to fade gently into the void, a gradual thinning of icy debris as you ventured farther from the sun. Instead, astronomers stumbled upon a cosmic cliffhanger. Roughly 50 astronomical units out, about 7.5 billion kilometers from the sun, the belt's population of icy objects doesn't just dwindle. It plummets. This boundary, known as the Kuiper Cliff, is so abrupt it's as if someone drew a line in the cosmic sand and told everything beyond it to vanish. Early surveys dismissed the drop-off as an observational fluke, a gap that would fill in once our telescopes improved. But when New Horizons sailed past Pluto in 2015 and kept going, its long-range scans confirmed the cliff was real and even steeper than we'd imagined. What makes this so baffling is how sharply it defies our models of solar system formation. The Kuiper belt should theoretically extend for hundreds of its icy leftovers from the solar system's birth slowly dispersing with distance. Instead, it's like hitting a wall. One moment you're navigating a crowded highway of comets and dwarf planets, the next you're staring into empty space. The most obvious explanation, a hidden planet lurking just beyond the cliff's edge, its gravity shepherding the Kuiper belt's outer reaches like a cosmic bouncer. This hypothetical world, often called Planet 9 or Planet X, would need to be several times Earth's mass to carve such a sharp boundary, a dark giant orbiting so far out it's escaped detection. But here's where the plot thickens. Not all scientists are convinced a planet is the culprit. Alternative theories suggest the cliff might be a fossilized edge, a relic from the solar system's violent youth. Imagine the sun forming in a dense stellar nursery, surrounded by sibling stars. One of those stars could have passed close enough long ago to strip away the Kuiper belt's outer layers, leaving behind this gravitational scar. Others propose a more subtle mechanism. Drag from the interstellar medium, the thin gas and dust between stars, might have eroded the belt's outermost objects over billions of years, like waves smoothing a shoreline. Then there's the timing problem. If Planet 9 exists, why haven't we spotted it yet? Surveys like Pan-STARRS and the upcoming Vera Rubin Observatory are scouring the skies, but finding a dim, slow-moving object in the vastness beyond the Kuiper cliff is like searching for a single unlit match in a football stadium using only peripheral vision. Every non-detection narrows the possible hiding places, yet the cliff's existence keeps pulling us back to the planetary hypothesis. It's a cosmic tug of war between what we see and what we infer. The most tantalizing clue might come from the objects that do survive beyond the cliff. a handful of extreme trans-Neptunian objects like Sedna, and 2012 VP 113 orbit so far out they seem untethered from the solar system's known gravity. Their paths loop into the void on elongated trajectories, as if something massive yanked them into bizarre dances. Whether that something is a planet, a stellar interloper, or a force we haven't yet named, one thing's clear: the Kuiper cliff isn't just a boundary. It's a message, a cosmic "Here be dragons" scrawled at the edge of our maps, daring us to look deeper. And that's the real magic of this mystery. The cliff forces us to confront how little we truly know about our own backyard. For all our probes and telescopes, the solar system's outer dark still holds secrets that defy even our boldest theories. Whether the answer is a hidden world or a forgotten chapter in the sun's early history, the Kuiper cliff stands as a reminder that discovery doesn't always mean finding something new. Sometimes it's about realizing how much we've overlooked. From dark matter's whispers to Venus's cryptic gas, these 29 truths paint a universe far stranger than we ever imagined. One where the most profound discoveries often begin as footnotes, glitches, or dismissed anomalies. Think about it. Every groundbreaking revelation we've explored started with someone refusing to look away from the data that didn't fit, the signal that shouldn't exist. Dark matter was once a scribble in the margins of galaxy rotation charts. Quantum entanglement was mocked as spooky action at a distance. Even the cosmic microwave background, now hailed as the echo of the Big Bang, was initially mistaken for pigeon droppings on a telescope. The pattern is unmistakable. The universe's greatest truths don't announce themselves with fanfare. They linger in the shadows, waiting for us to ask the right questions. This isn't just a story about scientific progress. It's a lesson in humility. For every mystery we've solved, a dozen more emerge, each more perplexing than the last. Take the Hubble tension. A discrepancy in cosmic expansion rates that threatens to rewrite our understanding of dark energy. Or Pluto's beating heart, a geological marvel on a world we'd written off as frozen and dead. These aren't just puzzles to solve. They're reminders that the cosmos operates on a scale and complexity that humbles even our boldest theories. The more we learn, the clearer it becomes. We've barely scratched the surface. Yet there's a thrilling undercurrent to this uncertainty. Every unexplained anomaly, every stubborn piece of data that refuses to conform, is an invitation, a cosmic breadcrumb leading to the next revelation. Consider how Oumuamua's bizarre acceleration forced us to rethink interstellar objects, or how Neptune's fiery poles upended our assumptions about ice giants. These aren't failures of science, they're its lifeblood, proof that the universe still has secrets to share. And with tools like the James Webb Space Telescope and next-generation neutrino detectors, we're finally building ears sensitive enough to hear its whispers. So what else is out there, lurking in the silence? Maybe the answers are closer than we think. The Phosphine on Venus, the missing water on Jupiter, the Kuiper cliff's stark boundary, each could be the first clue to something revolutionary. Or perhaps the next great discovery hasn't even registered yet, hidden in some overlooked dataset or yet to be launched probe's findings. That's the beauty of exploration. The universe doesn't reveal its secrets on demand. It waits for the curious, the persistent, the ones willing to question what everyone else accepts as fact. If there's one takeaway from these 29 truths, it's this: the cosmos thrives on contradiction. It's a place where black holes can evaporate, where time bends, where empty space seethes with quantum potential. Feeling small under the stars isn't a sign of insignificance, it's the first step toward wonder. Because the universe isn't just older, stranger, and more vast than we imagine. It's all those things than we can imagine, and then some. So stay curious, keep looking up, and remember, the most exciting chapters of cosmic history haven't been written yet. They're waiting, hidden in the next anomaly, the next whisper, the next moment someone dares to ask, what if we've been missing something all along? The universe hasn't shown all its cards, and that's what makes the game worth playing.